let's run through the circuit and we will try to note down the various node voltages. So voltage at this node is given by Vt, and this must be equal to S times Th minus of Ta, as we have already covered in one of our earlier videos. So Vt is the sensitivity of the J-type thermocouple multiplied by the temperature difference between the hot and the cold junction. Cold junction is at room temperature and Vt will be in microvolts. This is simply replicating the input voltage. So this is the voltage buffer, and then this is followed by the inverting amplifier where the feedback resistance is R10 plus R15 and the input resistance is R6. So you have VTH, which is the output voltage of this inverting amplifier, being equal to minus of R10 plus R15 by R6 times the input voltage, which is Vt. And so you can make the substitution for Vt over here, and we end up getting the expression for VTH. So note that VTH is one of the node voltages for this inverting adder circuit. So in this portion of the circuit, we have a voltage divider with equal resistances, and so voltage at this node should be half of the supply voltage. So this is at negative 2.5 volts, replicated over here by this voltage follower, and then assume that somehow we have managed to set this potentiometer so that the voltage at this node is minus of 0.273 volts. Now you have an 8590 IC temperature sensor. So the current I that is flowing from this branch is divided into two parts. One goes over here and we can call this as I1. The other one goes down, we can claim it to be I2, so that I is equal to I1 plus I2. And then we can frame the equation as 273 plus TA microampere, which is the current from the 8590, to be equal to I1. So I1 is the voltage between this node and this node. So this is at Vx, this is at virtual ground, and you have Vx divided by 10 kilo ohms. Similarly, I2 can be framed as Vx minus of minus 0.273 divided by 1 kilo ohm. So this is written over here, and then we can convert this into milliampere form because these resistances are in kilo ohms. Next you have Vx solving from this equation, resulting in 0.00091 times TA volts, and then this is followed by VAD. So this is an inverting amplifier, and we have negative of 10 by 10 times Vx, which is equal to VAD. So this must be equal to negative of Vx. So VAD is negative of 0.00091 times TA. Finally, we move on to the output, and you can see that this is an inverting adder, and so this will be minus of 1 by 10 times VAD minus of 1 divided by 10 times VTH, and so V out is given by minus of 0.1 multiplied by VAD plus VTH.